Hello Year 12 chemists, welcome to TP's Chemistry Cuts. In this video we look at how non-metal atoms covalently bond to one another by sharing electrons in pairs, and then go on to develop a procedure for drawing Lewis diagrams given a molecular formula.
What we're going to move on to now is where we are looking exclusively at substances made up of non-metals only. And it's very important you understand that these non-metals can be the same non-metal atoms, in other words in the elemental form, or they can be different in a compound form. So in all cases then what we're dealing with is covalent bonding. And to remind ourselves, with ionic bonding what's happening is you're reacting a metal with a non-metal. The metal has a less than half-filled valence level. The non-metal has a more than half-filled valence level, and so to gain extra stability, as we say, the metal will release electrons to empty its valence level out, and those electrons are transferred to a non-metal or one or more non-metals, and which fill their valence levels. And when that happens, both have gained stability because they're now comprised solely of filled levels. Okay? And that's the thing that's driving this. Is that their atoms are trying to fill their, or have only filled electron energy levels. Okay. Now the problem we have when we come to look at reactions that occur between non-metals, and they can be pretty reactive towards each other, so it's not a thing that's an alternative that's a second best, they'd rather react with the metal, they will react with each other quite happily, is that both non-metals in the reaction are wanting to fill their levels up. And so they can't do it by transferring electrons. They have to do something else. And what they actually do is share electrons in pairs. And that's what we call covalent bonding. Okay? And when they do that, they form molecules. What we'll do then is, first of all, describe the particle model for these molecular substances. And then we'll home in on our molecules. Once we've got our understanding of molecules up to scratch, then we'll have a look at the forces between those molecules. So it's going to be a two-step thing because we've not really dealt with these before. Okay? So let's put it down first of all. Now it's important to recognise that when I start talking about covalent bonding, that's bonding that's occurring within the particle, within the molecule. So let's get this right from the beginning. Molecular substances, the particle is a molecule, and you're taking these molecules, that's your building block, and you're stacking them all up together. And the force that acts between them are intermolecular forces. Okay? They're not covalent bonds. Covalent bonds occur within the molecule, holding atoms together to make your particle. Okay? So this is the force that we're dealing with between molecules. They're intermolecular attractions. And it's really important you have a clear distinction. It's a bit confusing because in this case, and this is the only case of the four types of substances we're going to deal with, there are two forces acting. Forces holding atoms together to make up the particle, then the particles being stacked up to make your substance, and it's forces that act between the particles. So at this point, we're just going to focus on these to say that they're there. Okay? We'll come back to them later because it's these types of forces that give the properties that we're going to be looking at to molecular substances. But first of all, we've got to understand what molecules are. Okay, so let's write it down. What I'm going to say is that each molecule in a given substance has the same number of each type of atom. They're connected by covalent bonds in exactly the same pattern, using exactly the same bonds. And they form molecules, and those molecules have exactly the same shape and size. So it's like building up a jigsaw puzzle with exactly the same shape of jigsaw piece. So you're just slotting them all in together. Okay? What we've got to rationalise is how the atoms join together, what type of bonds, because there's more than one, and in what arrangement. How do we work out how they're arranged given a formula? And that's what we're going to look at next. So that's our general model. We've got these fixed-sized groups of atoms. They're all non-metals. They're all sharing electrons in covalent bonds to give a fixed size and shape of a particle which then stacks up to make our substance. Let's have a look at how the bonding works. And hopefully this will start to make sense of why when you look at things like non-metals in their elemental form, they're not just a single atom. Okay. The simplest example we can take is hydrogen. In its gas form, standard form on Earth, as a gas, in its elemental form, it actually has the formula H2. Okay. And we can very simply show why. If we consider one hydrogen atom, how many electrons? One. How many does it want to get a nice filled level? Two. So what it can do, can look around and say we've got one H atom with its one electron, okay, and we see another H atom with its own electron. They can each put into their single electron into a pool, if you like, and share them. So what you end up with is, I'm using my colours again, too many of them probably. That. And if you look at each H atom, they now have two electrons. Okay, they're sharing them, but that doesn't matter as far as the hydrogen atoms are concerned. They've got filled levels, and that gives them that extra stability. And that's the way a covalent bond works. Now, if you've got something like this, a way of representing it is as a single line. Okay? So what we've got here is a shared pair of electrons. And that's a covalent bond. Okay? You can represent any shared pair of electrons, each shared pair of electron in fact, more precisely, by a line. That's quite acceptable. And this is an example where you've got one line. This is what we call a single bond. I'll just put the obvious there. So that's the very simplest example you can have of a covalent bond. Now you'll see I've used these things here where I've got an atom's symbol and I've put a dot by it. These are what we call Lewis dot diagrams for atoms. So they're Lewis atom diagrams, if you like. Okay, and we're going to use these a lot. So first, before we go on any further, we're going to go through these and show how they work for all atoms that we're going to deal with. Okay. Now, Lewis dot diagrams cover quite a range. What we're going to do for the moment is just home in on atoms. And the important thing about Lewis dot diagrams is they only show valence electrons. And you can draw them for any atom. So what I want to do is go to the second period and draw all the way across. Okay, so we're going to start off with lithium, and because they only show valence electrons, lithium has got one electron. Yeah. If we go to beryllium, we've got two. Now this is where you've got to take a leap of faith. Okay? When you're talking about atoms, if possible, electrons do not pair up. Okay? And each atom has got 4 sites around it. Okay? So initially, when you start putting electrons around an atom, as you're building them up, as you're going across the periodic table, then they will be in separate positions. Okay? So if we go to boron, which has got 3 valence electrons, you've got carbon, which has 4. We've got our 4 from before. Now we have to start pairing them up. That's where our 5th one goes. An oxygen. Fluorine. And then neon. Now, I could do the next row, but I'm not going to, because they would look exactly the same. So going down a group does not change the number of electrons, because we're only looking at valence electrons. Okay? Now this is just an exercise to show you this. We're not actually going to use the metals, but they do have their own associated Lewis atom diagram. So now we've got these, let's have a look at some other examples, because there's a few things to show you before we actually move on. Now look, we've looked at so far is where you've got 2 atoms that are the same. They don't have to be the same. You know that there are all sorts of molecules around there, like water and so on, where they're different. So let's take something that's very straightforward, where you've got different atoms. And I'm going to take hydrogen fluoride. Okay? So we've got H like that. I'll put it as green because fluorine's sort of a yellowy green colour. I'm start that way. And if we look at our diagram, we've got 7 valence electrons which are situated around an atom like that. Okay? Fluorine wants 8. Hydrogen wants 2. They both throw 1 electron into the pot, as we showed before. And what we get and now you can see hydrogen's got 2 electrons, fluorine has got 8. So all is happy. Or alternatively, you can write it like this. You must always write in non-bonded electrons. Okay? So that's the next thing to say. This are bonding electrons. These I call non-bonding electrons. You can call them lone pairs. I actually personally prefer to call them non-bonding electrons because that's what they are. Okay, so it gives you a better understanding of what you're dealing with. But there is nothing wrong with calling these electrons lone pairs. Now, this is what we call a Lewis diagram. Okay? And in Lewis diagrams, you absolutely must include these non-bonding electrons. Because a Lewis diagram is telling you where all the valence electrons are distributed in a molecule. And you're going to need to know that because later on we're going to use them to determine what the shape of the molecule is. So this is a Lewis diagram diagram. That diagram has three important things. Okay? It tells you where all the valence electrons are, and it tells you whether they're non-bonding or bonding electrons. So that's the whole purpose of Lewis diagrams. Now, before we start looking in great detail and working through how we get Lewis diagrams for a given formula, there's a couple of extra things to be aware of. Have a look at oxygen. So if we go, oxygen is here. Okay, it's got 6 electrons. So we've got that. We take a second one. Then, as before, we want to make up to 8 electrons for each one. We can share 2 like that. We're not there yet. What else can we do? Share the other ones, yeah, and they will do that. Okay, so it starts to look a bit messy, and you'll see different books will write this in different ways. Doesn't really matter. Once again, don't forget those non-bonding electrons. But this time, we've got 2 pairs of shared electrons. Okay. And this is what we call a double bond. Nitrogen, go one step further. No, extremely messy. So this is a triple bond. Okay, so the important thing is now that we can mix atoms up, and we can do single, triples and doubles. And it goes without saying, I can do an example later on, or we'll do an example later, where you can do mixed atoms on both double and triple bonds, as you'll see. So it's quite flexible. But that's the general basis of it. Now the problem with this is it's not only very messy, but if you get something a little bit more involved, it's not easy to see how this is going to work. And there's no need to worry about that, because we have a very general way of how you would go about, given a formula, how would you work out the Lewis diagram. And that's what I want to spend the rest of this lesson doing, and you can then practice them. Okay. Now, we're going to start with a straightforward premise, and this is that the molecules we're going to deal with have a single central atom with a series of surrounding atoms. Okay? And I'm actually going to call the central atom, and all the other atoms the surrounding atoms. Okay? So we're going to put that up on the board in a minute. Now, as part of the prescription for this standard, you will not get any more than 4 atoms around the central atom. Those of you that go on to do chemistry next year, which I hope is all of you, you'll see that that will get extended because you can actually get more than 4 in some cases. But this year you're going to have a central atom with no more than 4 atoms around it. They might be less, and we're going to look at how that works in a while. So we're going to work out a Lewis diagram for a random molecule. And so I'm choosing NOCl because it shows a number of things. Okay? Now, there's logic to this, but there will be steps in it, and you'll think, is that what happens? The answer is no. When things react, they don't do the things we're doing now. But what it does is it gets you the right answer in the end. So it's just a formalised system. It's not actually what happens in reality. Okay, so always keep that in mind. Now, if we're going to work out a Lewis diagram, what does the Lewis diagram tell us again?
It tells us the valence electrons within the molecule.
Yeah, so where the valence electrons are in the molecule. So what would be the most obvious thing to do first? What should we do first? Work out how many valence electrons we've got. That's the first thing we need to know, isn't it? Because we've got to start putting them around the molecule. Well, we need to know how many there are. And this is the one thing that after a while, a number of you will stop doing because you'll think it's not necessary. I can tell you it is incredibly important to do so. Because if you don't count the number of valence electrons, it's so easy to start adding in a few. Or if it's not working out quite, sort of rub a few out. And you'll get the wrong answer. Because you've either got too many electrons or not enough there. You have a fixed number of electrons that you've got to put around the molecule, so you're going to have to shift things around if they're not adding up properly. So the first thing we need is to calculate the number of valence electrons in the molecule. So that's our example. So nitrogen's got how many? Should look straight to the periodic table and count across.
6.
Okay, so I'm doing the work for you. So this is for N, O, and Cl. Okay? Now, this is the hardest bit, and the one you've got to be most careful with, or one of the hardest bits. We said over here that what we're dealing with is molecules where you have a central atom and a number of surrounding atoms. So we have to, in the next step, decide which is our central atom and which is our surrounding atoms. Okay? And it's simple rule. The one that's going to be in the middle is going to be the one that needs to share the most number of electrons, isn't it? Because it's going to need 1, maybe 2, maybe 3, maybe 4 atoms around it, because it's going to have to share every one of its electrons to try and get up to a filled level. So the first thing you should look at is the one atom with the fewest valence electrons is the one that's going to be in the middle, because it's going to need to share the most. Okay? Now, we'll look at an example in a minute where you will have a situation where you have 2 atoms that have the same number of valence electrons, which is the fewest. Which one do you choose? And if there's more than one atom that have the fewest number of valence electrons, you always go for the largest one, because the largest one will more easily fit things around it than a small one. Okay? Okay, when I mean the largest, when I say the largest, I mean the largest of the 2 that have the same number of the least. You see what I mean? We'll come to that in a minute. Okay, so in this case, we're looking at nitrogen. So nitrogen's our central atom, and we're going to put oxygen and chlorine around it. Okay, so this is central, Next step is very straightforward. Okay, so we're going to draw we've got nitrogen, chlorine, and oxygen, and we're going to, how many electrons is that? 2 bonds. How many electrons? 4. So we need to take 4 off our total, which I haven't actually added up here. So 18. Okay, so 18 electrons, and so we now have 14 electrons left. So you keep a tally as you're going along. It's really important. Okay. The next thing we're going to do is we're going to go around each of the surrounding atoms in turn and fill their valence level up. Okay? So we've got Cl and O. How many electrons do they need in each to fill their valence levels? To have filled valence levels, sorry. Chlorine and oxygen. Anyone? How many electrons do they need to have a filled level? 8. So if we look at chlorine, chlorine's already got 2 in that single bond. So we need to put 6 around it in pairs. Okay? So we've got N, O, and Cl. So to fill chlorines up, 1, 2, 3, 4, 5, 6, 7, 8. And then oxygen, you need another 6. And that fills that one up to 8. And we've used 12. So our tally is now down to 2. Okay, so we had 14 here. We put 6 round that, 6 round that, and so I've got 2 left. Okay. Those last electrons can only go one place. Where? The central atom. They've got to go on the central atom. So you put them in pairs on the central atom. So the next thing is we need to put those 2 remaining electrons, okay, are placed on the central atom. Okay, so we're going to put our 2 remaining electrons there. So we now have no electrons left. But as you've already picked up, that isn't right. Something's not right about it. The fact that oxygen has got 6 electrons, it's now got 8, whereas this one's got 7. This one's not got enough electrons. This isn't right. Things haven't been distributed properly so that all atoms have filled their valence level. And that's the whole point, remember. The reactivity is for an atom to fill its valence level. This isn't going to react if it's not going to fill its valence level, but it has reacted, so it has filled its valence level. So this is not right yet. Now, this is where you've got to take the leap of faith. And I said that what we're going to do may not be what's going on in reality. We've got to move some electrons because it's not right as it stands. Now, out of chlorine and oxygen, which is the one that showed double bonding before? Oxygen. Oxygen formed double bonds because it had 6 electrons. Okay? Whereas chlorine's got 7. Which is the more likely to move a pair of electrons if we had to move it? Oxygen, because it does that. It actually forms multiple bonds. And so what we actually do is we move a pair of non-bonding electrons from one of these atoms, and we'll talk about that in a minute, into a bonding position. So you're creating, instead of having a non-bonding pair, that suddenly becomes a bonding pair. Okay, so let's do that. So this is the last step in a way. Not every time do you need to do this. It's only sometimes. And it's only if the central atom does not have a filled valence level. By the way, one thing sounds incredibly pedantic, but when you're drawing the dots, you see how I'm doing sort of like a circular motion to make proper dots? Do that. There is a tendency, particularly among boys, to just do do, 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 do. And you'd be surprised how when somebody's rubbed something out on the page, a bit of stuck-on rubber or eraser piece looks like an electron. Whereas if you do it like this, it's quite clear where your electrons are. As I say, sometimes they can be awful. It only takes a few seconds longer to do it that way, and you're guaranteeing that the marker will see exactly where the electrons are. So what we're going to do then is we're going to move that one. Okay? So now we've got if you look at each atom in turn, you'll see chlorine has got 2, 4, 6, 8. Nitrogen, 2, 4, 6, 8. And oxygen, 2, 4, 6, 8. We've used exactly the right number, 18 electrons. Why? Yeah, so 18 electrons, and everything adds up. If you don't count the electrons, it's so easy to get to this point and think, oh, I'll just add a couple of extra in, that won't matter. If you've done that, it means it's now 2 minus, because you've added too many electrons. Okay? And this is the correct answer. Okay? Now, the question one or two of you may be thinking is, why do you do it from there and not there? There is one thing that you need to remember. Never ever, and this will solve all your problems, never move electrons on group 17 elements into bonding positions. Okay, so never do this for group 17 elements. So never do just group 17. Just group 17. Last step with group 17 elements. So by that we mean fluorine, chlorine and bromine. Never do it with those.
Wow.
Because what you're saying is these atoms, okay, they've got 7 electrons. You're expecting them to share not just 1, but 3. Because they've got to 8, but they formed a double bond. So you've actually asked them to share 3 electrons. It's not going to work. Okay, so it never happens. You never ever form double bond to group 17 elements. Doesn't happen. Whereas 16 and 15 you can, and 14. Okay. So that's that. Should we try another one? Don't all get too excited. Yes. So, many of these you'll be able to do without having to go through this. But I would put it to you, if you saw that, you wouldn't know how to start. For a start off, a number of people would put oxygen straight in the middle, because it's been written out like that. And we always write it out like that on purpose, so that you actually go through the proper steps. Okay? So always work it through. If it's something you've not come across and you're not sure, go for it. I want to do the same thing, but with a simple molecule, so that you can see that in fact, when you do this, you can actually, some of these steps don't apply. Okay, so what I want to do is, I'm going to do 2 more, because I've got to show 2 things. Okay. First of all, let's do a simple one, just to show how a simple one works. Okay. CO2. You know what the structure of it is, but should we do CO2? Or H2O? Something like that? Anything? Which one do you want? CO2. Okay. So CO2. So the first thing again is to count up the number of valence electrons. So carbon is how many? 4 plus 2 times 6, which is 16. Okay? Which one's going to be the central atom? Carbon, because it's got the fewest valence electrons. Okay? 4 versus 6. Yeah? So you can have carbon with 2 oxygens around it. So if we now draw in 2 bonds, 16 goes down to 12. Yeah? We can now put in 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Everything's gone. Okay? We've only got 4 electrons here. We need 8. So the obvious thing is, let's move one of these into a bonding position. So this actually might answer your question for you. Okay? What do we do with the next one? Are we going to move one from here or from here? This one. It's just intuitive, isn't it? You're going to put it from here because it's going to be easy to do that. Okay? And that's CO2. So you see, I jumped through lots of steps. And when you get through, you get used to this. Let's do H2O, shall we? Okay, once again, you've got 2 times 1 plus 6, which is 8. So you go oxygen in the middle, 2 hydrogens either side. So you're going to have 2 lines. That goes down to 4. 1, 2, 3, 4. Remember, hydrogen only ever has 2 electrons to fill its level, so it's always going to be an outside, a surrounding atom. I'll put that in. Note, H is always a surrounding atom. This year, that's the proviso, group 17 elements are always a surrounding atom. Okay? Now that second one is a year 12 only. In year 13 things change a bit, but let's keep things simple for this year. Do one more. How about that one? Sure. How many electrons?
4, 6, no, wait, yes.
4, 5,
4, 5, and 7.
Okay. Around 16. Which one's in the middle? Carbon. Carbon's always in the middle. Always. Okay. So we're going to put F and N. Okay. So put one there, one there. That goes down to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Gone. Now what do I do? So, from where? I'm going to start moving electrons around. Which one? Nitrogen. Okay. Next one? Nitrogen. Again. Because it's group 17. Never ever move them from group 17. Never. I think you're ready to try for yourselves.